Today we're going to discuss more on linear systems and invertible matrix. So in this discussion, we will show how the inverse of a matrix can be used to solve a linear system, and we will develop some more results about invertible matrices. Okay, so we have number of solutions of a linear system. So in this in the previous discussions, we made that statement that every linear system has either no solution, exactly one solution, or has infinitely many solutions. So we are now in the position to prove these fundamental results. So let's have theorem 1.6.1. So here we have a system of linear equations as 0, 1, or infinitely many solutions. There are no other possibilities. So, um, if let's say that you have um, you have a matrix A times coefficient x, which is equal to B. Okay, uh, let's say that this would be a system of linear equations. Exactly one of the following is true. You have the system has one solution, or the system has exactly one solution, okay, or the system has more than one solution. So in this case, the proof will be complete if we can show that the system has infinitely many solutions in case of 3. So let's assume that ax equals b has more than one solution, and we have also to let, okay, uh, x of 0, okay, is equal to x of 1 minus x of 2, okay, where the x of 1 and x of 2 are two distinct solutions. Because x of 1 and x of 2 are distinct, the matrix x of 0 is non-zero. So moreover, we could have uh, a x of 0 is equal to a times x sub 1 minus x sub 2, which is equal to a x sub 1 minus a x sub 2, which is equal to b minus b, which is equal to 0. Okay, if we now let k be any scalar, then you have a times x sub 1 plus kx sub 0 is equal to a x sub 1 plus a times k x sub 0 would be equal to a x sub 1 plus k times a x sub 0, which is equal to b plus k 0, which is equal to b plus 0, which is equal to b. But this says that x sub 1 plus k x sub 0 is a solution of ax equals b. Since x sub 0 is non-zero and there are infinitely many choices for k, the system ax equals b has infinitely many solutions. Okay. So let's have solving linear systems by matrix inversion. Um, we have studied two procedures for solving linear systems. We have the Gauss-Jordan elimination and the Gaussian elimination. The following theorem, okay, provides the actual formula for the solution of a linear system of n equations in n unknowns in the case where the coefficient matrix is invertible. So you have theorem 1.6.2. If A is invertible n by n matrix, then for each n by 1 matrix B, the system of equations Ax equals B has exactly one solution, namely x is equal to the inverse of A times B. Okay, so let's have an example. Okay, consider the systems of linear equations. You have that one. So in matrix form, this system can be, of course, be written in the form of ax equals b, where, oh, excuse me. Okay, where our a here, okay, our a would be, you have one, one, two, one, two. It should be one, two. Uh, one, two, three. You have two, five, three. Then you have 1, 0, 8. Okay. Then our x would be, you have x sub 1, x sub 2, x sub 3. And our b would be 5, 3, 17. Okay. So in what do you call this one? The first thing that we have to do is we have to determine the inverse of a. Okay, so I let you to do the uh, step-by-step process of the getting the inverse of a. Okay, and I want you to verify, okay, that the inverse of a in this case would be, you have, let me check, you have, in this case you have negative 40, 16, 9. Then you have 13, negative 5, negative 3. Then you have 5, negative 2, negative 1. Okay. So you can pause the video for you to get the step-by-step process of getting the inverse of A. Okay. Now, in this case, take note that from the theorem, okay, the x here would be a the inverse times the b. So in other words, you have to multiply negative 40, 16, 9, 13, negative 5, negative 3, 5, negative 2, negative 1 by the b, which is 5, 3, 17. Which in this case, the product would be 1, negative 1, and 2. In other words, our x, okay, x sub 1 would be 1, our x sub 2 would be negative 1, and our x sub 3 is equal to 2. So keep in mind that the method for this example only applies when when the system has many equations as unknowns and the coefficient matrix is invertible. Okay, so let's have linear systems with common coefficient matrix. So frequently, one is concerned with solving sequence of systems. You have uh, ax is equal to b sub 1. You could have ax is equal to b sub 2. Then you have ax is equal to uh, b sub 3, and of course so on to ax is equal to b sub k, for each of which has the same square coefficient matrix A. If matrix A is invertible, then the solutions, of course, would be here in this case. So you have uh, x sub 1 is equal to uh, the inverse of A, then b sub 1, then here x sub 2 is equal to inverse of A times b sub 2, then here you have uh, x sub 3 is equal to the inverse of A, uh, b sub 3, and of course in this case you have uh, x sub k would be the inverse of A times b sub k. It can be obtained with one matrix inversion and k matrix multiplications. An efficient way to do this is actually to form a partition matrix. So you have here the partition matrix. You could have A partition uh, B sub 1, partition B sub 2, that's 2, partition up to B sub k. Okay, so in which the coefficient matrix A is augmented by all k of matrices b sub 1, b sub 2 to b sub k, and then reduced 1 um, to what we call this one, reduced row echelon form by, of course, we can do that by Gaussian elimination or Gaussian Jordan elimination. In this way, we can solve for all k systems at once. This method has added advantage that it applies when a matrix A is not invertible. So let's have an example. Okay, solving two linear systems at once. Okay, so you have solved the systems, that one. So for in this case, we have actually what you're going to do here. As you can see, the A and B are the same except for the left side, the right side of the equation. So what you're going to do here is, of course, we are going to make this one in a partition system. So you have 1, 2, 3, 2, 5, 3, 1, 0, 8. Then partition, you have 4, 5, 9. And the second partition, you have 1, 6, negative 6. Okay, so what you are going to do here is reduce this matrix to reduce row echelon form. Okay, now you can pause the video for you to reduce the left side, okay, to row echelon form. Okay. And I want you to verify that the reduced row echelon form would be you have 1 0 0 0 1 0 and 0 0 1. Then you have 1 0 0, and then you have 2 1 negative 1. Okay, so that is our matrix. So it follows from the last two columns that the solutions of the system, okay, so for A, our x sub 1 would be 1, x sub 2 is equal to 0, and the x sub 3 is equal to 1. And for B, our x sub 1 is equal to 2, x sub 2 is equal to 1, and our x sub 3 is equal to negative 1. Okay. So let's have properties of invertible matrices. Okay, so up to now, uh, show to show that n by n matrix is invertible, it has been necessary to find a square matrix B such that you have uh, AB is equal to the inverse, and the elementary matrix, not elementary matrix, but it's the B times A should be its identity. So the theorem 1.6.3, okay, show that if we produce a square matrix n by n B satisfying either condition, then the other condition holds automatically. So you have here, let A be a square matrix. If B is a matrix satisfying BA is equal to I, then B is equal to the inverse of A. Then if B is a square matrix satisfying AB is equal to I, then B is again the inverse of A. Okay, so let's have the equivalence theorem. We are now in the position to add two or more statements to the foregiven uh, theorem 1.1.5.3. Okay, so we have 1.6.4, which is equivalent statements. So if A is an n by n matrix, then the following are equivalent. So A is invertible. Ax equals 0 has only one trivial solution. The reduced row echelon form of A is I sub n. A is expressible as a product of elementary matrices. Ax equals B is consistent for every n by 1 matrix B. And then we have Ax is equal to B has exactly one solution for every n by 1 matrix B. So it follows from the equivalency of the part E and part F that if you can show that Ax equals B has at least one solution for every n by 1 matrix B, then you can conclude that it has exactly one solution for every n by 1 matrix B. Okay. So let's have theorem 1.6.5. Let A and B are square matrices for the same of the same size. If AB is invertible, then A and B must also be invertible. So in our later discussion, the following fundamental problems will occur frequently in various contexts. So the fundamental problem is, let A be the fixed m by n matrix. Find all m by 1 matrices B such that the systems of equations Ax equals B is consistent. So if matrix A is invertible matrix, theorem 1.6.2 completely solves this problem by asserting that for every m by 1 matrix B, the linear system Ax equals B has the unique solution x equals the inverse of A times B. So if the matrix A is not square, or if A is a square but not invertible, then the theorem 1.6.2 does not apply. In this cases, the matrix B must usually satisfy certain condition in order for Ax equals B to be consistent. So that's what we have to um, bear in mind. Okay, so let's have an example determining consistency by elimination. So what conditions must B sub 1, B sub 2, and B sub 3 satisfy in order for the system of equations to be consistent? And the system would be on written below. So in this case, you have what to call this one? We have to augment. Okay, the matrix, you have 1, 1, 2, B sub 1. Then you have 1, 0, 1, B sub 2. And then you have 2, 1, 3, B sub 3. Okay, so of course, we can uh, augment this one. Okay, you have mm, you have to uh, negative 1 times the first row, then added to the second row, and negative 2 times the first row, then added to the third. Okay, again, let me state once again. You have negative 1 times the first row, then added to the second row, and negative 2 times the first row, then added to the third. Okay, so in this case, we'll have a resulting of uh, you have 1, 1, 2, B sub 1. Here you have 0, negative 1, negative 1, B sub 2 minus B sub 1. Then you have 0, negative 1, negative 1, B sub 3 minus 2 B sub 1. Okay. Now, in this case, you have to multiply the second row by negative 1. Okay. We have to multiply second row by negative 1. So you have here, you have 1, 1, 2, B sub 1. Then you have 0, 1, 1, B sub 1 minus B sub 2. And then you have 0, negative 1, negative 1, B sub 3 minus 2B sub 1. Okay. Then in this case, you have to uh, the second row would be added to the third row. Okay, the second row would be added to the third row. So you have uh, 1, 1, 2, b sub 1, then 0, 1, 1, b sub 1 minus b sub 2. Then you have 0, 0, 0, b sub 3 minus b sub 2 minus b sub 1. It is now evident from the third row in the matrix that the system rather has a solution if and only if b sub 1, b sub 2, and b sub 3 satisfy the condition that b sub 3 minus b sub 2 minus b sub 1 equals 0. Or, in this case, you have b sub 3 is equal to b sub 1 plus b sub 2. So, to express this condition another way, okay, which is ax equals b, is consistent if and only if B is a matrix in the form of, you could have the B is equal to, you have B sub 1, B sub 2, and B sub 2 plus B sub 1 plus B sub 2, rather. B sub 1 plus B sub 2. Okay. And that's all for this presentation, linear systems and invertible matrices. Thank you very much.